I, Umashankar Tripathi, would like to welcome you back on the GATE Academy English channel. Okay, so we are here to continue with our live series of GATE 2021 new additional topics. Okay, so here in this series, in this section, what we are doing, we are covering the steam turbine and the gas turbine topics, which has been recently added in GATE 2021 syllabus. Okay, so in that, what we have covered till now. So before that, first let me introduce myself. So who am I? So my dear students, my name is Umashankar Tripathi, and as you can see on the screen, as you can here see on the screen, that our topic is steam turbine and gas turbine, which is added in 2021 GATE syllabus. Okay, so in order to help you cover this portion and in order to boost your preparation for GATE 2021 examination, we are here having this series in which we are trying to cover whatever new thing has been added in GATE 2021 syllabus with respect to the thermodynamics part. Okay, so steam turbine and gas turbine here we are seeing, and as you can see on the screen, this is my name, Umashankar Tripathi, and I am currently a PhD scholar at IIT Roorkee. PhD scholar, you guys sometimes know us as research scholars. Sometimes know us as research scholars. Okay, so you can call me a research scholar at IIT Roorkee. That is also the same thing only. Okay. So before getting into this PhD program, I have completed my MTech from IIT Roorkee itself. And as far as the GATE history is concerned, as far as my GATE is concerned, I gave GATE in 2014, and in that I had 65.66 marks with All India rank of 916. On the basis of this GATE score and rank, I took admission in MTech program of IIT Roorkee and successfully completed it in 2016. Okay. From then onwards, I have entered this PhD program from IIT Roorkee, and currently I am a student of IIT Roorkee. So I gave once again GATE in 2015 as well. In that, I got 77.02 marks with All India rank of 643. All India rank of 643. So this is somewhat about my GATE history. Okay. And as you can see on the screen, I have been into this GATE teaching from past 8 years, even before I gave my GATE. So 8+ years I have been into this profession of mentoring students for their GATE preparation and helping them in a way. So as you know, we at the GATE Academy is having more than 50+ centers across the various cities of India. So before this lockdown, we usually had our offline sessions, offline classes. So at that time, I have been teaching across the various centers of the GATE Academy across the nation. Okay. Okay. So this is briefly about me. Now let's start what we have come here for. So we have completed till this much. We have completed till this much. Till this much we have completed. We have completed till this part. We have completed till this part. Okay. So in this series, what we have seen, firstly, we have started with the steam turbine. Okay. We have seen that steam turbine is a combination of nozzle and moving blades. Okay. Then we have analyzed the nozzle in first session. We had an introduction about what is new addition, what we are going to see in this session, and we had a brief classification of what kind of turbines are there and how questions can come from this topic and all. So every session is very, very important. If you are here directly, if you have not seen the sessions before this session, then please subscribe our the GATE Academy channel and find these videos. You will be finding them in our the GATE Academy channel. Okay, so please subscribe it and go on and find this. Okay, so in these three sessions, we had covered with the flow through the nozzle, and this is a compressible flow also. So this topic is also added. This topic is also added in GATE 2021 syllabus. So we can say we have also covered this topic in almost 90%, for gate point of view. Okay, compressible flow we have completed in the Gate Academy Hindi channel in 100%. All of things, particularly about compressible flow, we have completed in the Gate Academy Hindi channel. So if you are comfortable with Hindi language, you can go and see about the Gate Academy Hindi channel. You will find the compressible flow videos there. In the further sessions, we have analyzed the kind of blading, velocity triangles, efficiency part, and everything. So firstly, we have seen the impulse turbine part, which kind of blading impulse turbine is having, what are the differences, how we can obtain the work done, efficiency, gross efficiency, carryover coefficient, and everything in all possible respects. Okay, so in the last lecture, we have also completed the reaction turbine part, and we have concluded our last session with the reheat factor. So today we are going to just finish with the steam turbine, and then we'll be entering to the portion of gas turbine. Okay, so till this point we had already completed all the things about, as we can say, all the things about the steam turbine. So those who are live and have attended the previous lectures can respond to me that everything is clear or not. We had a day off on Sunday, so I hope you have seen some questions of these steam turbines as well. So I hope if you have seen all the sessions, then everything is going good. So we have concluded with the reaction turbine. So there are some more things which can be asked from this topic, So we are going to cover with that also. Okay. So see why we are covering this, because this is what we have seen in theory of machine also. So with less effort, we'll be covering more. In the less effort, we'll be covering more. So I think we must cover this also. Governing of steam turbine, because 1 mark, 2 mark theory question can come. 1 mark, 2 mark theory question can come from this topic also. So governing, so it's somewhat related with governors. Governors we see in theory of machine. Part. Yes or no? Those who are live can respond to me while I am having a sip of coffee. Okay. So governing of steam turbine means what? We are going to see some governors. Governors. So I hope if you have covered theory of machine subject, we had covered with the governors. The governor topic was also added in GATE 2016. So let us just simply briefly talk about what governor works, so that we can build our theory in this steam turbine part also, so that we can cover all those 1 mark, 2 mark question that can come from this theory part. Okay. So what is the function of governor? So governors are used, it's a device which is used to compensate for the load variation. So whenever there is load variation, try to understand this, whenever there are load variations, these load variations are accompanied with speed variations. As you can assume, whenever the load decreases, the speed increases. Obviously, whenever the load on something in some system has been decreased, okay, we can say the speed of the system is going to get increased. Okay. Similarly, when load increases, what happens to the speed? Speed decreases. So we cannot 100% control the load variations. We cannot 100% control this load variation. Okay. So if we have to, what we want? We want a speed constant. What we want? We want to have constant speed. Now somebody will say, sir, why we want constant speed? Now you imagine we have a steam turbine, and it is not giving you constant speed. So will it be able to produce electricity? Because this speed, this rotation is going to get converted into electricity in the generator part, which is the headache of electrical engineer. Our work is to give constant, as a mechanical engineer, our work is to give constant rotation to the electrical engineers so that they can produce their electricity from there, and then it's their headache what they will do, what they will not do. So we will hand over to the electrical engineers after we give them the constant speed of the shaft of the steam turbine. Okay, so we want to have what? We want to have constant speed. We want to have constant speed. So in theory of machine, you see two kind of these devices which compensate for which provide you with constant speed. One is flywheel and one is governors. So flywheel are used for intra-cycle fluctuations, means due to the varying torque generated at the crank. Okay, so to compensate for the speed variations caused due to intra-cycle variations, we apply flywheel. But the fluctuations, if they are inter-cycle, mean out of the cycle, like load, because we cannot control our load. Okay, so if the variations are outside from somewhere outside from the cycle, somewhere outside from the cycle, then we will call it as intra-cycle fluctuation. Then we will call it as intra-cycle fluctuations, inter-cycle fluctuations. Sorry. So governors are utilized to give us or compensate or deal with the variations of speed caused by the load variation, that are inter-cycle variation. Okay, so generally what we see in theory of machine part, what we see in theory of machine part, so we generally see centrifugal governors, like Porter, Proel. Yes or no? We are not going to get deep into this theory of machine thing. We are trying to develop some theory. For our steam turbine purposes. Okay, so generally we see centrifugal governor. Sometimes we also see spring control governor like Hartnell governor. Okay, so we are not going to analyze these governor things, but for basic understanding, so that this video is clear to you. So for this basic understanding, let us have a diagram. In order to save some time, I have taken the screenshot from the book itself. So we are going to see it here, that how a governor works. So little bit we are going to see. So what happens in a governor? So this is the steam turbine. As you see it. Okay, this is what a steam turbine. So from this bevel gear arrangement is what? That is also you see in theory of machine parts. So in bevel gear, what is happening? Bevel gear connects. Okay, bevel gear connects the two shafts which are inclined to each other. So here they are at 90 degree. These two shafts, if you see, this is the shaft of the governor. This is the governor shaft, you can say. Okay, and this is the shaft of the steam turbine or rotor of the steam turbine. So this is the shaft of steam turbine. Okay, so these two governor shaft and shaft of the steam turbine, as you can see it, they are perpendicular to each other. They are what? They are perpendicular to each other. So they are connected by means of a bevel gear. They are connected by means of bevel gear of equal number of teeth and equal diameter. So let's say D1, let's say D2. So these two gears are having same diameter, same number of teeth. So it means these two gears are rotating at the same speed. So in that case, we can call it also mitre gear. You might have heard this. So mitre gear is a special case of bevel gear. Where the two gears are at 90 degree and they are having the same number of teeth as well as same diameter. Okay. So here, can we say if this is rotating with n RPM, this is also rotating with n RPM. So usually we do this arrangement so that so that our governor rotates with the same speed as of the speed of steam turbine. Is that understood? Those students are live who can respond to me. Is that understood? Tell me yes or no. Tell me yes or no. Very good. So now, so now, so now, as this shaft is rotating at of the same speed, as this shaft is rotating at the same speed of that of the steam turbine shaft, we have this fly balls. We have this fly balls. So let's say their mass is m. Their mass is m. So there will be some centrifugal force upon it. There will be some centrifugal force upon it. So let me call it omega. Instead of telling it n, let us take term omega so that we can relate here also. Otherwise, every time we have to say that n is increasing, then omega is also increasing. So let's talk about it as omega. We all know omega is 2 pi n by 60. 2 pi n by 60. So let's say if n is increasing, so omega is increasing. So if the omega of steam turbine is increasing, omega of steam turbine is increasing from a certain value, so what will happen? What will happen? This centrifugal force will increase. This centrifugal force will increase. This centrifugal force will increase. Okay. So if the centrifugal force increases, what will happen? What will happen? These fly balls will try to move away from this axis. Is that true or not? These fly balls will try to move away from this axis as this is increasing. So this fly balls. So let's say let take like this, that we having our equilibrium position. So the figure you are seeing. So let's say this is the equilibrium position. We desire this much speed of the turbine. And if our turbine runs at this much speed, we are happy. If our turbine is running at this much speed, we are now very, very happy. Got it or not? Okay, we are happy. Okay. Now, if due to some variations, let's say load decreases, let us do like this. So let's say due to some variation, the load decreases. So the load decreases, what will happen to omega? It will certainly increase. So when omega increases, this omega mr, omega square, we call it centrifugal force, this will also increase. So when this will increase, this fly balls will try to move away from this axis, So if you feel it, when these trying to move away from the axis, this sleeve will go up, this sleeve will go up, and when this sleeve will go up, here is a fulcrum or a hinge. Here is a fulcrum, or you can see a hinge. So when this sleeve will go up, this lever will go down. And you can see there is a wall. This is the wall. Where is the wall? I am highlighting this. So this is the wall. Okay, this is the wall. So what will happen? When this lever moves down? This wall will move down also and will reduce this passage from where. This is the passage. See, yes, there can be many reasons. Of the load fluctuation. There can be many reasons because of what the load fluctuates in a steam turbine. Okay, it might be some generator issues. Okay, because see, when we are in a practical conditioning, now we are going towards some practical things. Now we have assumed that sir, this much RPM we require, so this is the amount of steam is entering. But you see, there can be many things. Sometimes what happens due to some generator issues, like generator want to increase this much capacity of electricity, like your generator is sending your electricity to some wire grid. Okay. Now, sometimes what happens, you at your home put some illegal means of extracting electricity. Sometimes people do not these kind of things. So they will put a wire over the grid, and they will somewhat take electricity illegally, right? So when these kind of things happen, load on the grid increases. Load on the grid increases. When the load on the grid increases, the power requirement of generator varies. Power requirement of generator varies. All right. So power requirement of generator varies. So there it will try to extract. It will try to extract more power from the turbine. Okay. Okay. So what will happen? We require constant speed from the turbine. Okay. But sometimes due to this electricity thing, our steam turbine load on the steam turbine reduces and a shaft tries to move at faster speed, and vice versa of it also happens. Vice versa of it also happens. All right. All right. So now coming back to the point. So if we feel the load decreases, omega increases, so we can certainly say that these fly balls will try to move away from the axis. And when this fly ball tries to move away from the axis due to this fulcrum, this lever will move downwards, and this valve will somewhat close partially some of this some of this passage. You can see, you can observe this passage. So from this passage, steam is coming like this. From this package, steam is coming like this. Steam is coming like this and going to the steam turbine. Going to the steam turbine. So if valve moves downward, it will somewhat restrict some of the passage of this stream, some of this passage of the steam. So when the valve moves downward, this passage is somewhat more closed. So the flow of steam will decrease. The flow of steam will decrease. And since the steam flow decreases, since the steam flow, mass flow rate of the steam decreases, we know the power is m dot. Okay, we know that power is m dot Vw1 plus Vw2 into U. We have derived all this in the previous session. So if we vary m dot according to the load, our power generation, our power will be varied. Yes or no? As we see in theory of machine, governors, what governors do, by controlling the supply of fuel, it compensates for the load variation. Okay, so when the valve move downwards, some mass flow rate will be reduced, and again the equilibrium speed will be reached. Now understand this. Now understand this again. So let us copy this figure once more time. Okay. So now if I say, just give me a second. Okay. So we are copying it here. In order to save your time as well as ours, I have taken this screenshot from the book of Dr. Pikinath, Power Plant. Okay. It's a good book. Okay. You also can read through it. Okay. And usually in GATE examination, these kind of standard books are referred to create questions. Okay. Now see. So again, let's say due to some reason, the load increases. Now when the load increases, what will happen to the speed? Speed will try to decrease. So now, as we have seen it, so let's say this is the equilibrium position. This is what? This is the, let me a little bit enlarge this figure so all of you can see it very nicely. So now if we say the load increases, the speed decreases, and let's say this is our equilibrium position. Okay, this is our equilibrium position. So this is our equilibrium position. If we say it and the speed decreases, so you can say, sir, this mr omega square is also decreasing. So when this mr omega square decreases, these fly balls will try to move towards the axis. So if you see it, if these fly balls try to move towards the axis, towards the axis. So you can observe the sleeve will move downwards, the sleeve will move downwards, and when the sleeve will move downwards due to this fulcrum, lever sleeve will move downwards. Just feel it, sleeve will move downwards, then this lever will go upwards, and this wall will go upwards, opening more of the passage. And since more passage is there for the flow of the steam, more mass flow rate will be flown to, more speed will be flow, more mass flow rate of steam will be obtained at the steam turbine, more steam will flow and enter into the steam turbine, and hence as we have the more speed, more power will be generated, and speed will again go to its equilibrium position. So this is generally how our governor works in any condition. So I tried to explain it, these governors with respect to steam turbine. Okay, you can further analyze it, you can further see that which kind of governors are there, what is a watt governor, what is a Porter governor, what is a Proel governor, what are the differences, what are the formulas, and all those things you can see in your theory of machine. And as we are covering here for the new syllabus, I am expecting that you have already did this governor part in theory of machine. So I am doing it with respect to steam turbine. With respect to steam turbine, I am creating some theory for you. So how a general governor works, is that clear or not to all of you? Is that clear or not to all of you? Those who are live can respond. Those who are live can respond. Now, what can be asked from this? This is all theory of machine. But what can be asked? What can be asked from a steam turbine point of view? So this can be asked like types of governing for a steam turbine. What are the different types of governing for a steam turbine? So we have first one as throttle governing. Throttle governing. We have what? We have this throttle governing. Okay. So throttling is a process. Why it is called as throttle governing? Because in this somewhat the steam is throttled. In this somewhat the steam is throttled. So see, in this what happens? We use this kind of governing happens. This kind of governing happens usually when the load decreases. When the load decreases. Okay. So when the load decreases, we have seen the speed tries to increase, the speed increases, all right. So when the speed increases, what will happen to this valve? This is stop valve. Okay, this is called as a stop valve. Okay, here this is called as stop valve. So when the speed increases, just realize it, when the speed increases, this valve will try to move downwards. This valve will cover or moves, let's say, downwards in the respect of the figure I am explaining. Okay, if this figure is made with some other respect, then it may be moving up. Okay, so I may say stop valve partially closes the passage. This will be more correct English. So partially closes the passage. What it will do? It will partially closes the passage. Is that true or not? Is it true or not? So stop valve partially closes the passage. Okay. So now due to, why we calling it throttle governing? So due to the restriction, what we can say, due to the restriction in the flow of steam, steam gets throttled. What will happen is steam gets throttled from, let's say, from pressure from or let's say steam gas throttle. Okay, now tell me, what is the meaning of throttling? We already have seen it in our classical thermodynamics, which is already into GATE syllabus. So what is this throttling? What do we call it? Why what is throttling? So it is a method of reducing what is generally throttling. So throttling, so in throttling, what will happen? Pressure reduces and enthalpy remains constant, and enthalpy remains constant. Yes or no? Remains constant. This is what we have seen in classical thermodynamics. As I said, we will be using the concept we already know. All the session, if you go and watch all the sessions from the compressible flow to everything, we have taught you with the very basics of concepts. Continuity equation, sometimes Bernoulli equation, sometimes isentropic equation, PV gamma is equal to C, that equation. Okay. Okay, so we are trying to use the general concepts of thermodynamics and fluid mechanics to teach you all this. Okay, velocity triangle we have made with the concept of fluid machinery we already had with us. So today in this lecture, we are applying the concepts of somewhat theory of machine and trying to understand the things. Okay, so throttling process, if you know it, so it is a process of decreasing the pressure at constant enthalpy, and you might have also know that this is a irreversible process. It is a irreversible process. So now you can also have this idea, that due to this throttling, some irreversibility is coming into our system. And whenever we say irreversibility comes, we have some loss. We'll be having some loss. Okay, so what loss happens with throttle governing? What loss happens with throttle governing? What loss happens due to the throttle governing? So our ideal is specific work output decreases. Our ideal is specific work output decreases. So due to this throttling, why this throttling is happen? And when throttle governing comes into picture, mostly when the load decreases, because throttling is a process which happens when some fluid is made to flow through restricted passage. We have seen all this. In basic classical thermodynamics thing. So there is nothing new. So this what has happened in throttle governing, when the load decreases, the speed increases, and the stop valve moves in a way that the passage is partially closed, and the steam is made to flow through that restricted passage, and hence somewhat throttling process happens here, due to which irreversibility came. And with that irreversibility, what is our effect? Our ideal specific work output decreases. So how this decreases, specific work output decreases? So you can have this idea, or we can in general say that, sir, this is irreversible. No, as this is irreversible, so something irreversible happens into our system. Something matlab means we were seeing frictionless process. Now friction came. So definitely it will cause some losses to us. So from throttle governing, one mark question, or some statement, correct statement, incorrect statement, or identify or match the following kind of questions. Theory question can be asked from here as well, that in throttle governing what happens. So you can say in throttle governing why it happens, when it happens, and what are the causes of it. So now somebody will be having this confusion, sir, how I am not able to understand that, sir, how ideal specific work output decreases. So for that again, I have I have taken the screenshot of a very good book named as written by Dr. P.K. Nag on the power plant, for the power plant. Okay, it's a very nice book, very good book. Okay, now see. So here I have taken the screenshot just to save some time of yours, because this is a theory part. You may feel bored also, but what to do? It can be asked, so we have to see it. Okay, we have no other option. Okay, so the live students can respond. Okay, now see, before what this one point is representing, the pressure before throttling happens. So this is our P1. And at this point we have this enthalpy. This is the HS diagram. So we have this enthalpy, let's say H1. So if throttling doesn't take place, so from this boiler, this is boiler pressure that we usually call it P0. This the topmost line, it is a boiler pressure, and this is our condenser pressure, the bottommost line. Okay, so ideally what should happen in a turbine? The pressure should be dropped from 1 to 2s. 2s represents isentropic condition. Okay, so if throttling is not happened, without throttling we are getting this work output, specific work output, our specific work output from a steam turbine in ideal condition, where isentropic expansion is taking place. So we are having this work output as H1 minus H2S. But we are now dealing into the practical condition, and you see due to this governor, this throttling happens. So you can see a dash line here. Irreversible processes are represented by dash lines. So this is our 3. So now due to throttling, due to this throttle governing, what will happen? Due to this throttle governing, what will happen? Our pressure will be reduced from P1 to P3. Okay, as you can see, this is the throttle. After throttle, this line you can see, I am marking it by red pen. Okay, this line. So this line represents somewhat lower pressure from the boiler pressure. Okay, so steam coming out from the boiler once get throttled, so its pressure is reduced. So in actual, what is happening? That is steam entering the steam turbine at lower pressure than the boiler pressure. So due to that, now what will be the work output after throttling? Ideal work output. Even that is also ideal. Now the entry of the steam work output, now it is also ideal. Because we are considering isentropic expansion from 3 to 4s. Okay, so now the entry to the steam turbine is at P3 pressure. And as you see that, as we have told you, that the throttling is an isenthalpic process. So enthalpy, there will be no enthalpy loss here. Enthalpy will be same. At 1 and 3, enthalpy will be same, but now as the expansion we have assumed to be isentropic. If we draw a straight line here, so now our this is the 3/4. This is the actual ideal process. If it happens, this is the actual ideal process. So work output in a ideal condition in throttle governing, when throttle governing took place, so you can see that it is H3 minus H4S, which is certainly less than H1 minus H2S. You can see H1 minus H2S is this, somewhat this. Okay, so H1 minus H2S is more than H3 minus H4S. H3 minus H4S. So can we say this, that ideal specific work output decreases due to this throttle governing? Due to this throttle governing, is that fine or not? Understood what throttle governing is? Understood what throttle governing is? Tell me. Tell me. Understood what throttle governor is? Those who are live can respond to me. Those who are live can respond to me, please. Those who are live can respond to me. Tell me. Tell me. Is that clear or not? Is that clear or not? Throttle governing. How the work is being reduced. So even a numerical can be framed from here. Even a numerical can be framed from here. Okay. 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 So this kind of things, these are the things which generally people do not teach in steam turbines. Okay, but I feel that this is also important. This is also an important part. Okay, this is also important part, because here multiple concepts, multiple subject concepts are applying. Okay. Okay, so multiple subject concepts are applicable in this discussion. So it can also be a topic from which question can be asked. Okay, now see. We want to have one more discussion with respect to the throttle governing. There is something called the Villen's line. Villen's line. This is not villain, but villains. Okay, so Villen's line is a plot. It can be asked into one number question. Is a plot of steam consumption. It is a plot of steam consumption. It is a plot of steam consumption with respect to the load. It is a plot of steam consumption with respect to the load. So again, in order to save some time, I already have taken a screenshot of this also from Dr. Pikenak's book. Now see, this is what a Villen's line. Okay, just to know you, just have some idea about Villen's line. So if it is asked in one number objective question, you can respond. Okay, so this is a Villen's line. This is a Villen's line. So this line gives you a linear relationship between the steam consumption rate, the rate at which steam is consumed, experimental line it is. So, so this line gives you the rate of steam consumption with respect to the load. So this is the relation. This is the relation of Villen's line. You can see it is a linear relation. That is why it is called as Villen's line. So from this you can see that with the load, the steam consumption increases, and it increases as proposed by the Villen's, that it increases in linear proportion, means a linear line relation. So here you can see A is what? A is no load steam consumption. When there is no load, this much steam is required. So that is A, this much is A, this much is A. Okay, and in this line, L is the load, B is the steam rate, P is the steam rate. So Villen's line, from using this, you can relate between A, B and L. A, B and L. So if it is asked in GATE examination, have some idea about it also. Trivial 1 minute topic it is. So we have covered that also. Okay. So throttle governing is clear to all of you. You can respond in the comment section. Those who are live, can you please respond to me? Now the next is nozzle governing. So when we use, first question is, when we use nozzle governing instead of throttle governing, so it is preferred. Remember this is can also be asked for one number. So this is preferred over throttle governing, in low load conditions, because as you have seen throttle governing has some losses, so efficiency definitely is going to get reduced, and as an engineer we do not want it. So throttle governing, we do sometimes nozzle governing. So in low load conditions, nozzle governing is preferred over throttle governing. Nozzle governing is preferred over throttle governing. So what happens in nozzle governing? So in this, we have some sets of nozzles. So we can say nozzles are made in sets, okay, are made in sets, and each set is controlled by different wall. Each set is controlled by different wall. Okay, so what you simply do, so let me show you a figure of nozzle governing, you will be able to understand even better. So again, for saving some time, I had this already ready for you. So now let's say, see, oh, okay. So in nozzle governing, as you can see here, we have some sets of nozzle. Connected to different walls. As you can see, this set is connected with wall. This set is connected to this wall, and this set is connected to this wall. So okay. So now at low load conditions, or when the load decreases, you can say, okay, what happens is speed price to increase. So we require to reduce the steam flow, or we want to reduce the mass flow rate of a steam. So in throttle governing, or in previous type of general governing thing, what we do in general governing thing, we do it by partially closing the wall, or the passage, due to which this throttling happens, due to which some loss occurs. So in order to avoid it, we do it nozzle governing. We sometimes do nozzle governing. Okay, so in nozzle governing, what we do, we simply close some set of nozzle. So when we simply close some set of nozzle, what will happen? The steam flowing through this set will be reduced, or will not go inside the turbine, and hence the steam consumption or steam flow reduces. Okay, so nozzle governing particularly is used over throttle governing in low load conditions. Got my point? So simply there is one more type of, let us move to the third type. These things are very simple, so we are not going to put some more time over here. So we are having bypass governing also. Okay, so you can see some objective question may be asked from this topic. Objective question may be asked from here, from these topics. So now we can do now the bypass governing as well. So as the name suggests, in bypass governing, what we do, so here you can see the screen again. There was some technical issue happened. Okay. So this bypass governing, as you can see it, so bypass means okay. Bypass means So firstly, this is used in overloading condition. So in overload conditions, what will happen? If there is overload, overload means what? Load increases. This happens, but overload means that load has increased to somewhat greater limits, to somewhat greater extent. Okay, so in overloading condition, bypass governing is used, and as the name suggests, so in overloading condition, speed decreases drastically. You can say speed decreases drastically. Speed decreases drastically. So if the decrease of the steam is very drastic, how will you control it? How will you control it? How will you stop this much reduction of speed? So you can say that we can use, sir, the bypass governing. We can use the bypass governing. Okay, so by bypass governing, we will bypass some more steam into the steam turbine, and hence the power generated by the steam turbine will suddenly increase, and we can meet this speed drastic decrease of the speed. Is that okay or not? Simple, simple. So these can be asked in one number question where bypass, what is the meaning of it? So I think it is understood to you. Live students can respond. Is it clear to you? And the last kind of governing is emergency governing. Emergency governing. So I think you know the meaning of emergency. Emergency. So in case some emergency happens, within our steam turbine, within our cycle, within our arrangement, then we will use emergency governors. Emergency governors. Okay. So in every steam turbine or in every steam turbine cycle, we have some emergency governing system. We have some emergency governing system. Okay, we have some emergency governing system. Okay, so emergency governing, what it will do, it will suddenly stop the flow of the steam, and it generally happen, it will stop the flow of the steam. So definitely power generation will be stopped all of a sudden. So we do it generally when the speed of shaft increases, or speed of the shaft increases, we can say, or speed of the shaft exceeds 110% of rated speed, of the rated or specified speed, what we can say. Okay, what we can say. So emergency governing, what will happen? The flow of the steam will be completely stopped. So flow of the steam completely stopped. So you can say our steam turbine would be shut down. And we do it in the conditions where, generally we do it in the condition when the speed of the shaft exceeds 110% of the rated speed. So if we talk about India, what I have told you, that in India the speed is 3000 rpm, because in India we are using the system of 50 hertz. We are using generator which are working at 50 hertz frequency. Okay, so in India we are having this rated speed generally of the steam turbines is 3000 rpm. Okay, so when emergency governor will come into picture? When emergency governor will generally come into picture? When the speed of the shaft somewhat exceed 110% of the rated speed, means it will come into picture when the speed exceed over, in India I am talking 3300 rpm. 3300 rpm. Okay, got my point. So somewhat if the speed increases or reaches this value of 3300 and try to increase even further, we will have to or we can say the emergency governor will come into play. Governor will come into play and will suddenly stops the flow of the steam, and hence shut down, and any probable accident will be avoided. For sure will be avoided. All right, all right. So what are the other conditions? Other conditions in which, what are the other conditions in which, what are the other conditions in which, what are the other conditions in which we can say, what are the other conditions in which this emergency governor will come into play? So if first condition is, we have first condition already, we have when the speed of the shaft exceeds 110% of the rated speed. So what could be the other condition? If lubrication system fails, we can say somewhat that's something happens and lubrication system fails, and you know it. Steam turbines are big power plants, NTPC. We are trying to get our job into it. We are trying to work into it. So if you see a NTPC power plant in India, it's a very big, very huge power plant. Okay, so if lubrication system fails and still your turbine is working, huge losses can happen, huge wear and tear can happen, and your whole plant can go into the maintenance mode or can be out of function. Okay, so it will be a huge loss. So if anything happens and lubrication system fails, emergency governor will come into picture and will stop the flow of the steam and will shut down the whole system. Then you can repair it and you can again start it. That will be a better thing to do. What else? What else? So if balancing is not proper, balancing, there is a topic in theory of machine. Okay, balancing is also added in GATE 2016. Okay, so balancing is not proper. Balancing is not proper. Okay, sometimes somewhat more vibrations are coming, or some balancing mass has been out of the place. Somewhat something has happened. Practically many things can happen. So if our balancing mass goes out of order or balancing is not proper, then also we have to stop the turbine and we have to correct it before something accident, before some kind of accident happens. Okay. Okay. So in that condition also, our emergency governor will come into play and will stop the turbine. What else? What else? Sometimes it happens that condenser becomes too hot. So these are all the general conditions in which we use the emergency governor. So emergency governing is kind of safety precautions. It's kind of safety measures one should take in a steam turbine power plant, so that there is no accident, there is no bigger losses. So there is no big losses in our power plant. Okay. So what can be other conditions? So obviously, if any of this happens, condenser become too hot, means the supply of cooling water is not proper, or somewhat like that happens. So we can say we have to suddenly stop the steam turbine in order to save this big equipments from a bigger or a major wear and tear. Okay, so we use emergency governing. So is the governing of steam turbine clear to all of you? What are the methods? What is the general way? So if our objective question comes from here, will you be able to answer? So those who are live can respond to me. So we are covering this steam turbine in all possible respects. So if anything asked from you, you will be able to answer. Got it or not? Tell me. Those who are live can respond. Those who are live can please respond. And meanwhile, please do not forget to subscribe, like and share the GATE Academy. If you are liking all this series is very useful for all the students preparing for GATE examination, because I hope you guys have covered You guys have covered already, which is already been in GATE syllabus. So this is a new edition. If you watch this session completely on the GATE Academy channel, it will be very, very beneficial to you. Okay. Okay. So now there is one more thing. We call it as dummy piston. So we are not going to analyze this, but just if some question or objective question asked from here, you will be able to answer. So dummy or balanced piston. Dummy or balanced piston. Okay. So as the name suggests, this thing help us. This thing help us. This thing help us in the balancing of our steam turbine. This thing help us in the balancing of our steam turbine. This thing helps us in the balancing of our steam turbine. So what happened? We have seen all this in the previous sessions. In impulse turbine, we have seen impulse turbine. In impulse turbine, the rotor moves due to the impulsive action of the steam. So in this, axial force are less. So this is to compensate for or deal with the axial forces. As you know, steam turbine are axial flow devices, and so are the gas turbine that we are going to enter. And so in gas turbine, we are not going to analyze the velocity triangle. We are not going to do the analysis of the blade because we have already done that in case of steam turbine. In case of steam turbine, okay, the same is applicable for gas turbine, but gas turbines are not generally impulse kind of. They are reaction turbines, and in that reaction is usually less than 50%. Reaction is usually less than 50%. Okay, so if our same steam turbine concepts you can apply, what is going to change? We will be telling you, but we are not going to make the velocity triangle and everything again. Okay, okay. So in this dummy or balanced piston, they compensate for axial force. Okay, so impulse turbine, axial force is less. So generally dummy piston is not used. So again, you can see a question can be raised from here. So dummy piston is not used in impulse turbine generally. Dummy piston is not used in impulse turbine generally. Although in reaction turbine, what we have seen that in reaction turbine with combined action of impulse as well as reaction. Combined action of impulse as well as reaction happens in the moving blade. Okay, so due to this reaction force into picture, axial forces are generally high axial forces. In the previous session, we have seen all this, and we have seen the use of Parsons turbine, 50% reaction turbine. So why do we prefer what we have seen? Why do we prefer Parsons turbine? Why do we prefer these Parsons turbine? So we do prefer this Parsons turbine because in Parsons turbine, the axial force are somewhat nullified. Okay, so reaction turbine due to high axial forces. So sometimes the axial forces are so high that our rotor can come out of the shaft while in work, while producing power. So if this happens, a huge accident can take place. Human life will be in danger. So for that, we use dummy piston. Okay, so reaction turbine, high axial forces are there. So use of dummy pistons are generally there, which are applied just like a balancing mass. So it will take care of the high axial force in the reaction turbine, and will reduce the chances of this huge accident that the rotor may come out of the shaft. So you can imagine while working, if a steam turbine rotor comes out of the shaft, what will happen? Okay, so we generally use this dummy piston in case of reaction turbine and where axial forces are very high. So this much we are going to see on in this, because if objective question analysis is not required, as far as we are already are seeing much more. Okay, so this much is sufficient. So last thing of this steam turbine is critical speeds. Just one last thing in this steam turbine section is critical speeds of steam turbines. So this word also you have seen while you study the topic of vibration in generally, which is taught in theory of machine. So critical speed of steam turbine. So this critical speed, we have seen it in theory of machine. So again combined of combination of multiple subjects are used in this analysis of a steam turbine. We have seen till this session that we have applied the concept of classical fluid mechanics, we have applied the concepts of classical thermodynamics, and now we have applied some concepts of theory of machine. That's why we say that this topic is so very beautiful that a questioner, the IIT professors who want to frame questions of the GATE 2021 examination may obviously can choose from this topic. Okay, so critical speed of steam turbine. Critical speed of steam turbine is what we have seen in the theory of machine vibration part. So just quickly we are going to cover it. So let's say we have a shaft. This is our steam turbine shaft. Okay, so in practical conditions, generally, the axis of the shaft in practical condition generally, this axis of the shaft is not coincide with the axis of rotation. Okay, so there is always some eccentricity. We can call it as delta, or we can call it as E, or E, whatever you want. Let's call it delta. Okay, so there is always some eccentricity of the shaft from the axis of rotation. So let's call it delta. So we have seen all this in vibration part. So I am making it very, very quick. So let's say we have given some. It is rotating. So in practical condition, let's say it has some amplitude, or it has some deflection, a small deflection of y. So let's just quickly make the balancing of the existing forces. So there is a centrifugal force, and there will be a stiffness force. So force of stiffness will be S into Y. So if I deflect this shaft while rotation with Y, so we have this equation. So from this equation, we can certainly do what? Let's open the brackets. So we have my omega square plus m delta omega square is equal to S into Y Okay, so from here we can say that we have this. Let's say we have taken this y as a common, so it will be m omega square. Just see it, m omega square. Okay, so let's just call it E. Otherwise, you will confuse with the deflection, no? So we are calling it E. Whatever you may want to call this eccentricity, there is no problem at all. So let's call it E, no problem. Otherwise, some people will get confused here. So this is E, let's say. Okay, so we have this m omega square minus S, or let's just write like this. Otherwise, we have one more step will increase. So let's say S minus m omega square. Okay, S minus m omega square. All right. And here it will be left with me omega square. Here we will be left with me omega square. Okay, so if I take m omega square common here and will send it there, so it will be like this: S by m omega square minus 1. We have seen this relation in vibration part also. So from here we can say that Y is E upon and S by M is omega n square minus 1, omega n square minus 1. So let's just see it. This is our Y. This is our Y. So if you see omega is the speed of steam turbine speed, and omega n is under root S by M. That is the natural frequency. That is the natural frequency also. You call it natural frequency. So if omega becomes equal to omega n, it will be a critical speed. We call it a critical speed. And at this, what will happen? What will happen? You can see from this relation that when omega become omega n, Y will go to infinity. This condition you call in your vibration as resonance. So if Y goes to infinity, some accident may happen. Because deflection is reaching to infinity. You can imagine what will happen. So we must avoid certainly. We must ensure that our steam turbine do not run at. Our steam turbine do not run at is critical speed. All right. And as I have said that for E to be zero, omega should be infinity. See from the relation. Omega if infinity, Y is equal to E, or Y will be equal to E. Yes or no? Or we may say, see, we are putting infinity here, so it will be 0. So E will be 0, we can say. E will be 0. So if you want no eccentricity, you must run your shaft at infinite speed, which is not possible. So this is the critical speed. We must ensure that our turbine do not run. At this speed. Okay, so here we can have, so while designing that diameter, diameter of the shaft, this critical speed concept must be taken care. This critical speed concept must be taken care. Okay, it must be taken care, because you know this omega n is equal to under root S by M, or there is one more equation. We say G by delta. This equation we use in where? In theory of machine. So you know this delta is equal to 4L cube by 48 EI when the shaft is simply supported. You know all this, na? Now some concept are applying. So simply supported beam loaded at center. Okay, so from here I is equal to what? I is pi by 64 d ki power 4. So from here you can have the idea, you can have an expression for diameter also. So while designing the diameter of the steam turbine shaft, you must consider this also. So is that clear? Is that critical speed governing concept is clear to all of you? Say yes or no. Is this governing thing and the critical speed concept is clear to all of you. So hereby, I am concluding this steam turbine with this last thing, that if it is asked between the efficiency, so the efficiency in the same condition of parcel will be highest, D level and ratio we have seen, and the lowest will be of the two-row Curtis turbine. Okay. So this can also be asked. That whose efficiency is highest, whose efficiency is lowest. So with this last thing, let me conclude this steam turbine. Okay. So at this point in all this lecture series, we have been seeing this steam turbine in all the respects. So we have covered the compressible flow also in here. So steam turbine and compressible flow are completed from my point of view. Okay. So is that fine? Can we call it that, sir? If a steam turbine is, those who are live can respond. Sir, the steam turbine, if a steam turbine is asked to us in GATE to 2021, we will be able to answer it. Say yes or no. Those who are live can respond to me. So as you are responding, so can we say, okay, very nice. So we can say that, sir, yes, sir, with all this discussion, we can say that, sir, we will be able to solve the steam turbine question. We have seen almost all the things. Okay, almost all the things we have seen. All the things we have seen. All right. Okay. So let us now begin with the gas turbine portion. Okay. So this is also added in GATE 2021 syllabus. So the combined topic is steam turbine and gas turbine. So let us have a little bit. So here we are in this particular section. We are not going to analyze the gas turbine specifically, but we are going to analyze the gas turbine cycle. In general, ideal cycle, then we'll move to the actual gas turbine cycle. Because gas turbine as a equipment is similar to the steam turbine. It is also axial flow, so all the velocity triangles and everything we have seen already. All right, and also we have seen the compressor, not here, but compressors was there already in GATE syllabus. It was also added from GATE 2016. So in compressor, you see a axial flow compressor. So gas turbine follows the same kind of blading, same kind of velocity triangles as we see in axial compressors. Okay, so as specifically as far as for equipment is concerned, we are not going to analyze the gas turbine because it will become boring. We already have seen the same type of thing. As I was teaching the steam turbine, velocity triangles were quite similar what we have seen in fluid machinery. Okay, so again telling you that already in this series I have told all of that, so we are not going into that. So firstly, let us see what is gas turbine cycle. gas turbine cycle. So we are going to analyze the gas turbine cycle, and in later point of time we will see the actual gas turbine cycle. Okay, actual gas turbine cycle. Okay, so now in a gas turbine cycle, so there is a compressor. There is a compressor. What we have? What we have? So we have a compressor with us. We have a compressor with us. Okay, we have a compressor with us. So how it is going like? So we have a compressor. We have a combustion chamber. A combustion chamber. Okay, combustion chamber. Then we have a gas turbine, which is quite similar to the steam turbine what we have seen. Okay, then we have a condenser. Then we have, no, not condenser. Condenser is the term we use when condenser, boiler kind, evaporator kind of terms we use when we are dealing with two phases, when we are dealing in two phases. Okay, okay, we are dealing in two phases, but in a single phase we cannot use those terms. We cannot use those terms. So we use the terms like cooler, combustion chamber, heat exchanger when we deal with a single phase reason, when we deal in a single phase reason. So what happens in a steam turbine cycle? Sorry, what happens in a gas turbine cycle? So let's say this is 1 point, let's say this is 2 point, let's say this is 3 point, and let's say this is 4 point. Okay, so air or some gas. Okay, this is gas turbine cycle. This is also we call as, okay, gas turbine cycle. Generally we use air. Okay, generally we use our air or some gas, light gases. Okay, so as compared to steam turbine, cycle or steam turbine power plants, our gas turbines are lighter in weight, because see, the fluid you are handling is lighter. So definitely the arrangement will be lighter, not that bulky as you see in steam turbine. As you see in a steam turbine, the whole thing become very bulky because we are handling the water. And since we are handling the water, so the equipments are generally large. Okay, equipments are so much there. Okay, because we are handling the water, so the weight of the overall system goes very much. So in gas turbine, we see that we are using some lightweight gas or air. So these kind of cycles are used in aircrafts also. Okay, so it is called as aircraft cycle sometimes also. Aircraft cycle, aircraft power cycle, air power cycle. Okay, these kind of words are simply used with gas turbine cycles. So as we know, let's just quickly, because this is already there in GATE syllabus, for reaching to the actual turbine cycle, we need to analyze this. We are going to see actual turbine cycle. So for actual turbine cycle, for seeing this actual turbine cycle, we require to see all this. We require to see the ideal gas turbine cycle, which is called as Brayton cycle also, So what will happen in general, not ideal, not actual, if we talk in general. So what happen in compressor? The pressure of the gas, if air, so the pressure of that gas flowing through the compressor will increase. Then it will go to the combustion chamber. So definitely some heat addition will be there. 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 Some heat rejection will be there. Some heat rejection will be there. Okay, some heat addition will be there. Some heat rejection will be there. So whenever some heat addition, heat rejection take place, some work will be produced. So this gas turbine will produce some work also. Okay, this gas turbine will produce some work, omega T will produce some work, omega T. Okay, omega T, but part of this omega T will be required to run this compressor, because in the steam turbine case, the pump do not require high amount of work, but in case of compressor, almost 40 to 50% of whatever work produced by the gas turbine, whatever work is produced by the gas turbine is consumed. 40 to 50% of that is consumed is consumed by the compressor, is consumed by the compressor, okay, is consumed by the compressor. So from this WT, some WC will go to the compressor, some compressor work will go to the compressor. So if I cloud it, if I encircle all this, if I encircle out this, so what is actually coming out? What is actually coming out from here? What is actually coming out from this encircle? So we are getting our network. We are getting our network, which is turbine work minus compressor work, which is turbine work minus compressor work. Okay, turbine work minus compressor work. So we are actually getting at the end this network, that is turbine minus compressor work. And as we know, we are required to find the efficiency. So efficiency is what? Output. So what output we are getting? Turbine minus compressor work upon what input we are giving. So we are giving the input as heat addition. We are giving the input as heat addition. Okay, so this is the general system, general cycle. So let us just first understand the ideal cycle. So that is called the ideal Brayton cycle. A gas turbine cycle works on the Brayton cycle. Brayton cycle. Brayton cycle. So let us say what is ideal Brayton cycle. So let us see what is ideal. Ideally, what is our Brayton cycle? We have to see now. We have to see now. So this is all what you have seen also. This is all what you have seen also in your power plant, which is already in your GATE syllabus. But for developing or reaching to the point where we see the actual gas turbine cycle, we need to analyze this also. We'll need to analyze this also. So our ideal Brayton cycle will follow these, the air standard assumptions will follow these, the air standard assumptions. Okay, so our ideal Brayton cycle will follow air standard assumptions as well. Air standard assumptions as well. So the air standard assumptions are, we know it. So Cp, Cv, and gamma. Cp is, we know, specific heat at constant pressure. Cv is specific heat at constant volume, and gamma is the specific ratio of specific heat. So Cp, Cv, and gamma do not change with temperature, okay. Also, we consider that changes in kinetic energy and potential energy are negligible. Kinetic energy, potential energy are negligible. Okay, what else we consider? So we consider no pressure drop. We consider as there is no pressure drop, no pressure drop while our air, while air flows from heat exchanger, combustion chamber, okay, combustion chamber, cooler, and various ducts. Okay, so we consider that there is no pressure loss, but in actual condition there will be some pressure losses. Okay, while fluid flows through them. Okay, so if there is no pressure losses, so heat exchangers, combustion chambers, and are coolers coolers are considered as constant pressure devices are considered as constant pressure devices Okay, so heat exchanger, combustion chamber, and coolers are considered as constant pressure devices. All right, are considered as constant pressure devices. All right. Okay. Also, there is no heat loss. There is no heat loss. There is no heat loss when there is no heat loss during compression and expansion processes. During compression and expansion process. During compression and expansion process, there is no heat loss during compression and expansion process. So we can say that compression and expansion are isentropic. So this is what the air standard assumptions are. So firstly, we will have, see, now how this lecture series will flow. Firstly, we will analyze this ideal standard cycle, ideal air standard cycle, or ideal Brayton cycle. Okay, why we do it? Because only when you know what is the ideal condition, what is happening in ideal cycle, then only you will be able to get what happens in the actual cycle. Okay, so when we move to the actual cycle, we will see that these assumptions will be not no more valid. So if these assumptions or some of these assumptions are not valid, how to proceed, how to solve, we are going to see. But for that, firstly, we have to understand the ideal Brayton cycle. We have to see its special cases. Okay, we have to solve some questions of it also. Otherwise, you will not be able to get actual gas turbine cycle. And as far as gas turbine as a device is considered, as you see, previously in this lecture series, in the steam turbine part, I have not taught you the Rankine cycle, or we have not in very much depth analyzed the Rankine cycle. Okay, because there I already as a device, I have already as a device, I have explained the steam turbine in all the respects. So in the last, I will tell you that as a device in gas turbine, what changes you may follow or what you may follow. Okay, so again going through that velocity triangle will have no meaning because we already have seen all those things. So this will go very much boring. So here we are going to see the actual gas turbine, which was not in GATE syllabus previously. Okay, so as they have written the gas turbine, so I assume now actual gas turbine is also in your syllabus. The complete gas turbine thing, the complete gas power cycle is in your syllabus. So we are going to see, we are making our way, we are reaching to this actual gas turbine cycle thing. And there, for that, we require to have a better understanding of this ideal gas turbine cycle, that is ideal Brayton cycle. Okay, so you got this approach, what we are going to study now. The live students can respond to me. The live student can certainly respond to me. And meanwhile, I also request all of you to like and subscribe the GATE Academy channel. Share it with your friends also, so that they will get the maximum benefit. Because see, this is the new syllabus. Okay, this is the new syllabus thing. Okay, so certainly if you are preparing for GATE, this is very much important. Okay, although nobody can tell you with 100% guarantee that from this question will certainly arrive or not, but we have to see all these things. Okay, so do watch all the lectures in the series if you want to have completed. If you are seeing it in between one lecture you have seen, so you may not be able to understand all the things. You may not will be able to understand all these things. Okay, all these things. Okay. Okay, so do watch all the sessions, all the videos in this series, so that you have the better understanding. You have this better understanding. You have this better understanding. Okay, you have this better understanding. So first, let us make the PV diagram. In a steam turbine, I have not taught you about the PV diagram, TS diagram mostly. Okay, because there I was trying to teach you the steam turbine as a device, but here I am treating the cycle. And if you relate this cycle concept to your steam turbine cycle, you will have the idea. So kind of, if you watch this series, kind of complete old syllabus, new syllabus, everything is mostly covered, more or less. Okay. So now if we draw the PV diagrams, considering all these, so this is our PV diagram. This is our PV diagram. This is our TS diagram. This is our TS diagram, PV diagram, TS diagram. Okay. Okay. So from 1 to 2, what is happening? Compression is happening, and isentropic compression is happening. So you know, isentropic compression. Isentropic compression is showed by this kind of line. This is rectangular hyperbola. So from 1 to 2, pressure is increasing. So pressure is increasing. So in compression, volume will decrease. 2 to 3. 2 to 3 is constant pressure heat addition. See it here. See from here. 2 to 3 is constant pressure heat addition. So if constant pressure heat addition is taking place, so pressure will not change. Pressure will not change, but volume will increase. Volume will increase from 3 to 4. From 3 to 4, what is happening? Isentropic expansion is happening. So if expansion is happening, volume will increase, pressure will decrease, we know it. And 4 to 1 is constant pressure heat rejection is taking place. So in constant pressure heat rejection, pressure will remain constant and volume will decrease. So this is the PV diagram of ideal gas turbine cycle or ideal Brayton cycle, considering all the air standard assumptions. All the air standard assumptions. All right. Now see, if you see the tendency of the cycle, it is clockwise. So from the classical thermodynamics, we know in a work producing cycle, this tendency should go clockwise. So you can cross check. So this is definitely a work producing cycle. So if I make the TS diagram now, so we have two pressure lines. We have these two pressure lines over which the whole play is there, over which the whole play is happening. So let's say we have the two pressure lines like this. We have the two pressure lines like this. So from 1 to 2, what will happen? From 1 to 2, what will happen? So pressure is increasing, so temperature will increase, and as it is an isentropic process, so entropy will remain constant. Entropy will remain constant. Now 2 to 3, what will happen? Constant pressure, heat addition. Yeah, definitely. I will solve the regeneration problem. Okay, Ish. I will explain the regeneration as well as if you guys require, we'll solve some problem of regeneration as well. Don't worry. Okay. So 2 to 3 is there. 2 to 3 is there. Okay, 2 to 3 is there. This is the one next pressure line. So 2 to 3, what is happening? Constant pressure, heat addition is happening. So in heat addition, you know, temperature increases when constant pressure, heat addition takes place, the temperature increases and the entropy increases. This information we have from this classical thermodynamics. This information we have from the classical thermodynamics we read. So if you guys have observed, I have made this line a multiple times and reduced it and erased it. So why I am doing this again and again? Just because I want to have this 4 point. I want to have this 4 point above 2. I want to have this 4 point above 2. Okay, this we are going to use in the regeneration. So in 3 to 4, what is happening? 3 to 4, what is happening? 3 to 4, what is happening? Our isentropic expansion is taking place from 3 to 4. So entropy will remain constant, pressure will reduce, and so as the temperature will also reduce. Temperature will also reduce. So from 4 to 1, from 4 to 1, what is happening? From 4 to 1, what is happening? From 4 to 1, what is happening? Constant pressure heat rejection is taking place. Constant pressure heat rejection is taking place. Constant pressure heat rejection is taking place. So in heat rejection, constant pressure, temperature will reduce, entropy will reduce. So we will come back to our 1 point. And here also you can see, the tendency of the cycle, which is clockwise, which again gives you this idea that this is work producing cycle. So I hope this ideal PV and TS diagram is clear to all of you. This ideal cycle PV and TS diagram is clear to all of you. Why we require all this? Because we are going to compare it with actual turbine cycle. We are going to compare it with this actual gas turbine cycle. So that is why I am saying, firstly, we must understand, yes, T4 is greater than T2. While making TS diagram, please try to make like this, where from the diagram itself, you can see that T4 is greater than T2. Because in later stage of this section, we are going to see this regeneration thing. So regeneration will only can take place when T4 is greater than T2. Otherwise, it cannot take place. Okay. So that is why we are considering T4 greater than T2. So in future, we won't make any mistake. All right, Pawan? Okay, now let us move and find the efficiency of ideal Brayton cycle. So in order to find the efficiency of this ideal Brayton cycle, we are required to apply some basic concepts of general thermodynamics. So I hope all of you know some of the basic thermodynamic concepts. So we will apply those and you can recognize that yes sir, we know it. So we are just applying. Okay, so let us do it with the help of TS diagram. Let us do it with the help of TS diagram. So how I am making the TS diagram? First, we are making these two pressure lines. So from 1 to 2, compression is there, isentropic compression is there. So in compression, we know it. That's a temperature increase and entropy will remain constant as it is. Isentropic compression. So just take care that T4 will come above T2, T4 will come above T2, and here it goes at T1. So this is our cycle. This is our cycle. This is our cycle. Got it? This is our cycle. Got it or not? This is our cycle. So now let us apply some basic concepts. Let us apply some basic concepts of the thermodynamics, basic concept from the thermodynamics. So we are required to find the efficiency. So efficiency, as we have established, is turbine work minus compressor work. Turbine work minus compressor work upon heat added, all right. So if the turbine work, if I talk about here, so turbine work is H3 minus H4. From steady flow energy equation we can have this. From steady flow energy equation we know now, from steady flow energy equation. Okay, let me apply it if you do not remember it. So we have this turbine, we already have used it multiple times in our discussion of steam turbine. So let's say it is 3, and let's say it is 4, let's say it is 3, let's say it is 4. So HFE what? H3 plus V3 square by 2 plus Z3. So we are, what are our assumptions? That we are neglecting the kinetic energy and pressure energy. So let's just write the SFE once again. So V3 square by 2 plus GZ3 plus Q is equal to H4 plus V4 square by 2 plus GZ4 plus W. All right. So now as we have seen the assumption, just have a look at this assumption. So the changes of kinetic energy, potential energies are neglected. So just neglected. The process is considered to be isentropic, so there is no heat transfer, as it is written here. As it is written here, that no heat loss during compression and expansion. So Q we can neglect. So from here we can say the work of this turbine is H3 minus H4. So let's just put it. So we have this H3 minus H4. We have this H3 minus H4 minus compressor work. So if I say compressor work will be H2 minus H1, H2 minus H1, H2 minus H1. Similar, if you apply a steady flow energy equation between entry to exit of a compressor, H3 minus H4 is H3 minus H4 is H2 minus H1, H3 minus H4 minus H2 minus H1. Okay. Now what is this heat addition? So this heat addition is H3 minus H2, because heat addition is taking place between 2 and 3. So our heat addition will be H3 minus H2. All right. Is that all right? H3 minus H2, as you can see. So this is not from steady flow energy equation. From which concept I am directly writing the enthalpy difference. So if you know the general thermodynamics or the classic thermodynamics, so in a constant pressure process, how I am writing it? In a constant pressure process, heat interaction is equal to DH. In a constant pressure process, heat interaction is equal to DH or MCP dt. This is what we get to learn from the general thermodynamics, from general standard basic thermodynamics. So from basic thermodynamics, we use in a constant pressure process, del Q is equal to DH MCP dt. For constant volume process, we use del Q is equal to du, that MCV dt. Got my point or not? Got my point or not? So I have written this efficiency in terms of enthalpies, in terms of enthalpies. So let me just convert it in terms of temperature. So for ideal gas, air is an ideal gas. You want me to Pavan write SFE for compressor? Okay, let's do that also. So let's say we have a compressor. Okay, entry to this compressor is at one point, exit at second point. So we have H1 plus V1 square by 2. Can I not write this V1 square and all because we are going to neglect it? So I'm just writing H1 plus Q is equal to H2 minus WC. Why I'm putting minus here? Why I'm putting minus here? Because compressor work is the work done upon the system. Okay, in turbine the work done is by the system. So when we have the work done by the system, when we have the work done by the system, when we have this work done by the system, when we have this work done by the system, when we have this work done by the system, we take it positive. When we have the work done upon the system, when we have the work done upon the system, it is negative. So in a compressor, we have to give work. So work is being done upon the system. So I am writing here minus. So as the process is isentropic, there is no heat loss. So we can neglect this Q and we can have this WC as H1 minus H2, as H1 minus H2. Okay, okay, okay. Got it? Or sorry, H1 not H1 minus H2, but H2 minus H1. But H2 minus H1. So this is what I have written here. All right, Pawan? H2 minus H1. All right? All right? Okay. So now I am just going to convert everything in terms of temperature. And for that, we know enthalpy is a function of temperature for air. Enthalpy is a function of temperature for air. So everywhere we can use this expression H is equal to CPT, H equal to CPT. So just put it everywhere, just put it everywhere, just put it everywhere. So CP will be cancelled out because it will be in the numerator as well as it will be in the denominator. So we will have this equation like this: T3 minus T4, T2 minus T1, H3 minus H2 will become T3 minus T2. So if you have all these temperature values, if you have all these temperature values, you do not require anything else. If you have all these temperature values in an ideal Brayton cycle, you do not require anything else. You can have your efficiency. You can have your efficiency. Okay. So we are going to stop here in this session because now we have to develop this efficiency formula. So we will begin from this point in the next session that we are going to start from 1 p.m. today. So do come in the next session also. Please watch the next video also, because in the next video we are going to have the analysis of this ideal Brayton cycle. We are going to see this efficiency, what is the effect of changes of pressure on it. Okay, the pressure ratio thing. Okay, and we will be trying to cover the regeneration, the intercooling, the reheater, and then we'll see all of them combined. Then we'll go for the actual turbine cycle, that what happens in an actual gas turbine cycle. And lastly, we are going to see the components of the gas turbine cycle, and then we'll have the end of the all the series. Okay, so our 3 more sessions are left with us. We are going to have 3 more sessions, and in that 3 more sessions, we will conclude this series. So I hope those who are watching every session or coming live in every session are enjoying this series and feeling that this series is useful. Okay, those who are live can respond to me. Okay, and then if there is any doubt, you can ask me. Otherwise, we will end this session. We will end this session and we'll meet again in the next session, next live session. Please give your feedbacks in the comment section. Okay, thank you very much. So if you have not subscribed the GATE Academy yet, please do it. Please do it. Okay, and here on the screen, you can now see the email address. So if there is any feedback, you can give it. You can give it in the comment section also, and you can send us your feedback to this mail ID you can see on the screen. You can call us. You can visit our website to know what are the courses running in the GATE Academy. Okay. So to have all the notifications, to have the notification that what is new or what new lectures, some good lectures are on this channel, you can find. So please subscribe the GATE Academy English channel, as well as find the Hindi channel also, the GATE Academy Hindi channel we have also. Please go and subscribe that also, because in both of these channels we are giving you good information, good informative videos, okay, about what is the current scenario, also general videos sometimes at the GATE Academy we upload. So I request you, if you are liking this session, if you are liking this series, please go and subscribe it. And please ask your friends to do the same. It is absolutely free. It is not chargeable. So please help others, help other students, the needy ones who require to see this subject, okay, who require to learn this new topics. Please share to them also. Okay, so thank you. We'll meet in the next session. Thank you very much.